Good day everyone, I am Sir Slater Paul, and in this video, we will be discussing a subtopic of the rotational kinematics of rigid bodies, which is called rotation with variable angular acceleration. Our scope for today is within this topic only so that we can strengthen our foundation and learn how to properly solve problems regarding variable angular acceleration. I know this topic may be intimidating for some since it involves a bit of light integration and differentiation. So, my goal here is to simplify the concept and processes for you so that you can always be confident when faced with these types of problems. So, let's start. We begin with a light review regarding the concept of rotation. Rotation is defined as the motion of a rigid body in which the particles move in circular paths with their centers on a fixed straight line that is called the axis of rotation. The planes of the circles in which the particles move are perpendicular to the axis of rotation, which means that the plane and the path make a 90-degree angle. So, as you can see with this figure on the right, where there is an established 3D axis, the body rotates about the vertical axis, making it the axis of rotation. Its path is indicated by the pink circle that is perpendicular to the vertical axis, which satisfies the definition of rotation. If you've reached this topic in your engineering mechanics class, I assume that you are already familiar with straight line motion or rectilinear motion, where you were introduced to the concept of displacement, which is denoted by S, velocity denoted by V, and acceleration, which is denoted by A. Rotation also has these properties, only this time, instead of a straight path, the displacement, velocity, and acceleration of a rotating rigid body are along a circular path, which is really the only underlying difference. So for us to clarify that we are dealing with rotational motion and not rectilinear, we can simply replace the symbols that we use to denote these terms. Therefore, rotating rigid bodies undergo an angular displacement, which is now denoted by theta. They have an angular velocity, which is denoted by omega, and an angular acceleration, which is denoted by alpha. The standard units for these variables are as follows: radians for theta, radians per second for omega, and radians per second squared for alpha. Now, another similarity of these two types of motion is how the respective variables relate to one another. We know that velocity v is derived from differentiating the function of displacement s with respect to time t. We also know that acceleration can be found by differentiating the function of velocity with respect to time, or the second derivative of the displacement function. Furthermore, these two relations can be used to relate the three variables by eliminating the time component, establishing a third equation. These concepts also apply to rotation since these relations differ only in the symbols used, meaning they are mathematically identical. Therefore, angular velocity omega is found by differentiating angular displacement theta with respect to time, and angular acceleration alpha is found by differentiating omega with respect to time, or by finding the second derivative of theta. We won't be discussing how to derive the kinematic equations anymore since these three relations are just what we need to solve for variable angular acceleration problems. So the problems regarding this topic usually come in five cases. Cases 1, 2, and 3 are when the variables theta, omega, and alpha are given as functions of time, respectively. Case 4 is when a principal variable is given as a function of its adjacent variable. What this means is that it can be theta as a function of omega, omega as a function of theta or alpha, and alpha as a function of omega. Case 5, on the other hand, is when the principal variable is given as a function of its non-adjacent variable, meaning it can be theta as a function of alpha or alpha as a function of theta. We will only be focusing on the first three cases since these are the most common ones being asked. For case 1, where you are given theta as a function of time, you are usually asked then to find the value of omega and alpha at a certain time. Now your solution here would just be differentiation, wherein you differentiate theta with respect to time to find the function of omega, then differentiate again to find the function of alpha. Then you just simply substitute the given time for your required answer. For case 2, where you are given omega as a function of time, you are usually asked to find theta and alpha at a certain time. What you will do here is to integrate the function to find the equation of theta and also differentiate to find the equation of alpha. As you can see here on the left, we know that theta derives to become omega and omega derives to become alpha. Therefore, if we are given omega, we would need to go backward and forward to find our required equations, which is where integration and differentiation is utilized. And finally, for case 3, we are given alpha as a function of time. If you are asked to find omega and theta at a specific time, all you need to do is integrate alpha with respect to time to find the omega equation, and then integrate the obtained omega equation to find the equation of theta. If you're confused by this, it's just simply going backwards in the relation line as seen on the bottom left. So before we begin solving, let us first recall some basic differentiation and integration processes. Here we have the power rule, which shows that the derivative of a variable that is raised to an exponent n is found by bringing down n as a constant and then subtracting the exponent of the variable by 1. This is fairly straightforward, as you can see by the example below. Next, we have the power rule again, but this time for integration. This shows that the integral of a variable raised to an exponent n is equal to the variable being raised 1 degree higher divided by the value of n plus 1 plus an arbitrary constant c. But since we're dealing with definite integrals for this topic, we don't need to worry about c anymore. This rule is only applicable when n does not equal to negative 1, as seen on the example below. And as I've mentioned earlier, we would be dealing with definite integrals or integrals with limits. These limits are usually denoted with a and b, which are called the lower and upper limits respectively. For variable acceleration problems, a is where we put the initial condition of a variable that is given in the problem, and b is where we put the final condition of that variable in order to find our answer. Now here are the general steps in solving. 1. Write down the given function and its initial conditions. 2. Analyze which case you should use. And number 3. Differentiate or integrate accordingly. Please do not forget the initial conditions when integrating, as forgetting would surely lead to an incorrect answer. So para maisaulo na ito lahat guys, apply na lang natin ang ating mga tutunan sa pagsagot ng isang sample problem. So dito makikita nyo ang problem 1214. The rotation of a flywheel is governed by the equation omega is equal to 4 times the square root of t, where omega is in radians per second and time is in seconds. Theta is equal to 2 rad when t is equal to 1 second. Compute the values of theta and alpha at the instant when t is equal to 3 seconds. So para mahanap natin yung mga equations para dito, sundin lang natin yung mga general steps. Una, isusulat natin yung mga given. So, binigyan tayo ng function na omega is equal to 4 times the square root of t. Rewrite ko na lang to guys as 4t raised to 1 half since same lang din naman yan sa square root para hindi tayo malito sa pagsosolve. So, ano ba ang mga initial conditions? Ito guys, pag may nakikita kayong ganitong klase na sentence, theta is equal to 2 rad when t is equal to 1 second, kadalasan yan na yung mga initial conditions natin. So, sulat lang at theta equals to 2, t is equal to 1. So, magagamit natin yan mamaya. So, punta naman tayo sa step 2. Analyze which case should be used. Paano ba to? So, tignan nyo yung given function. Diba, omega yan is a function of time. So, automatic na case 2 yung problem at sakto pang pinapahanap both ang theta at alpha. So, alam na natin mag-differentiate at mag-i-integrate tayo. At dahil dito, simulan na natin ang step 3 which is yung differentiate or integrate accordingly. So, para makuha yung equation ng theta, recall lang natin na omega is equal to the derivative of theta with respect to time. So, rearrange lang natin tong equation na to since yung omega ang function of time. Pagsamahin natin yung omega tsaka yung dt. Then, integrate lang natin itong equation. So, sa part na to guys, may-utilize na yung initial condition na given sa problem. Ilalagay natin sila sa baba ng integral sign. So, ang initial condition ng theta ay 2, kaya lagay natin dito sa left side. Sa itaas niya ay ang theta variable lang. Sa right side naman ay ang time at alam natin na ang initial nito ay 1. So, lagay natin dyan sa baba, tas t variable lang din sa taas. After nito, substitute lang natin yung omega equation. So, magiging the integral of d theta evaluated from 2 to theta is equal to the integral of 4t raised to 1 half evaluated from 1 to t with respect to t. Then integrate lang natin guys. So yung integral of d theta is theta lang to be evaluated from 2 to theta. Then sa right side ay ilalabas natin yung 4 kasi constant lang din naman to. Since yung left side is for evaluation na lang guys, focus lang muna tayo sa right. So yung 4, i-multiply natin sa integral ng t raised to 1 half, which is t raised to 1 half plus 1 over 1 half plus 1. Tapos evaluate natin to lahat from 1 to t. So simplify lang natin. 1 half plus 1 is 3 over 2. So magiging 4 times t raised to 3 over 2 divided by 3 over 2. Yung 3 over 2 na denominator magiging 2 over 3 kapag ginawa nating multiplication. So magiging 4 times 2 over 3 times t raised to 3 over 2. Therefore, yung complete equation natin is theta from 2 to theta is equal to 8/3 of t raised to 3 over 2 from 1 to t. Simple lang yung pag-i-evaluate nito guys. So, isa-substitute lang natin yung upper at lower limits sa equation na in-evaluate nito. Thus, yung format is final condition minus the lower condition. Therefore, yung 2 at theta is isa-substitute lang natin sa theta, habang yung 1 at t naman ay sa 8/3 of t raised to 3 over 2. So, ang mangyayari dyan is magkakaroon tayo ng theta minus 2 is equal to 8/3 of t raised to 3 over 2 since kapag sinubstitute natin yung t sa t lang din naman yung lalabas, minus the quantity of 8/3 of 1 raised to 3 over 2. To simplify further, we have theta minus 2 is equal to 8/3 of t raised to 3 over 2 minus 8 over 3. Then makukuha na natin yung equation for theta, which is now 8/3 of t raised to 3 over 2 minus 2 over 3. So, underline lang natin, tas kunin muna natin yung equation for alpha guys bago tayo mag-substitute sa time. Mas madali lang to kumpara sa theta kasi direct differentiation lang. So, recall natin na alpha is equal to the derivative of omega with respect to time. So, substitute lang natin ang omega equation dito. Supply lang natin yung power rule. So, may 1 half na bababa, tapos yung exponent na 1 half ay mababawasan ng 1. To simplify, therefore, we have alpha is equal to 2t raised to negative 1 half. The only thing to do now is to substitute t that equals 3 in the equations that we have to find the answers. So, input nyo na lang to sa calculator guys para ma-double check. So yung final answer natin dito guys is therefore, when t is equal to 3 seconds, we would have an angular displacement of 13.190 radians and an angular acceleration of 1.155 rad per second squared. So check lang natin guys kung correct ba yung answer natin. So tama naman. Kaya this marks the end of our lesson regarding variable angular acceleration. Thank you so much for listening and see you next time.